Alright, should be another draft physics video presentation. Yeah, looks like it is. Alright, so do some comments. They're kind of trivial and uninteresting, but play along. And then we'll do something else. Play a couple of clips from a couple of different videos. So the pervy guy says another topic. So yes, I did go to that video. An interesting Feynman's thesis, doctoral thesis, I guess, for physics. And it does relate to a Sean Carroll clip that I'll play about what energy is, and it sort of fits together. So we'll do a little bit on the concept of energy. Anyway, it's all been bean counting. So CERN has discovered a smaller bean. So what? It's not really what they're doing, so it's really not, you can make simple arguments about CERN and particle physics. I guess I would argue that one of the arguments you make is that this is a highly technical experiment, and so a lot of what they're doing is filling in the gaps, the bits, to make it into drawing some sort of general information from very specific information. So you could get like a 1-inch square of hide from like a wildebeest, and then a little piece from on top of his head, and a little piece from here. You could get very specific, very detailed, but they're never going to really tell you what the wildebeest is. So, I can make lots of analogies for where CERN fails, in terms of it's highly precise and highly accurate, but it's not a very good instrument to see context. So kind of like a microscope, you have to be very sure about what you're looking at, or you won't interpret what you're seeing. You can look at squid tissue or human tissue or this or this. If I mix up the slides and you don't know the context, you could draw all kinds of conclusions about reality that would be incorrect because you didn't know what you're really looking at and the context in which you're looking at it. So I would say that most of these accelerator experiments where they say they're calling a particle, something a particle, a Higgs boson or this, that, on, or whatever, that they're not really seeing particles. They're seeing a consequence of energy distribution and how energy moves through what patterns it has, based on how something explodes or something breaks or something interacts. And they're calling the energy a particle, which is sort of a mistake. It's not getting the context right. So, but whatever. I'm not a big fan of generalization statements. It's just not very helpful. Concise statements describing things are really great, but they sort of have to be really accurate to be great. And so generalizations are a little sloppy. Like I said, it's not really bean counting. He looks like a superhero from the 70s. Whatever that. I didn't know there were 70s superheroes. They invented some in the 70s. Stringy hair man. Yeah, cool. Whatever. Would you say that that in physics there's only two states, either together or apart? That sounds kind of like a girl thing. Wants to get everybody married. It's a nice, simple statement, and yes, sort of what I'm arguing is that, proximity, moving things together creates more energy just by the nature of how matter functions. It's what things do, in terms of trapping it. So you realize you have energy by taking something that was going across the whole universe and making it go across two little things. Obviously, it's going to have more impact. It's going to hit things more often. So the more often you make the energy hit something, the more often you make it hit something, the more energy it appears to be. And the less energy it is, the less often it hits something. So proximity just increases the amount of interactions that the force allows us to have with each other. So in a sense, you could say, yes, things that get close together create energy by creating more interactions. But I don't want to get too Star Wars about it. Either physically together or physically separated. You get close together physically in contact physically, so what is fusion? Well, the difference is the idea of whether you're taking an atom, all right, and you can do two things, right? You can put two atoms together. You can look at it two ways, right? You take the two atoms, you smash them together, and you create one atom, and you have some little pieces left over. Or I'm trying to think of two things you combine commonly: peanut butter and jelly. you know, and you might have, it's hard to say you'd have some jelly or peanut butter left over, so that doesn't really work. There's probably some other example of where you put two things together and there's some spare parts left over. You take a vacuum cleaner and a blender and you mix them together to make a oysterizer or something, a garbage disposal or some other kind of thing. And you'll have some parts left over. Some of the parts are superfluous or redundant, so you throw those out. Now that would be fusion. And then fission would be, you take the big thing, something that's already made, like the vacuum cleaner, and you turn it into two different devices. Can't really turn into a sucker and a shooter, but you make two different things out of it, something out of the hose and something out of the motor, and then you have leftover parts that you don't need, and so those become energy. So in most of the nuclear reactions, you're only taking a tiny percentage of that E equals mc squared thing. You're taking a tiny percentage of the fact that you have more bits in proximity. Like each atom would have three pieces, next to each other, and this atom would have three pieces next to each other, and the thing you make is only going to have five pieces next to each other. So one of the pieces is away, so now there's less interactions totally, so you've lost some energy to the system, to the world, to the universe. And the vice versa would be, you have 3, 4 things, let's say 5 things, and you split them into 2 and 2. So now you have still 4 that are involved with more proximity, but you let that 5th one go. So you'll release some energy again. So that's how I would explain it. But this is a kind of phraseology that's a little too, it's too much of a metaphor. Together, it's just kind of the wrong kind of language, but that's all. I'm just, the metaphor is really quite correct. I guess it's just the exact phrasing of it just has too much of the, whatever, love physics style, just doesn't, CERN is a cesspool of contamination. Well, I don't, that doesn't say much. What does it have, coronavirus or something? I mean, what's your argument? It's dirty there. I don't know. I just don't think it's a useful statement. All right, this is something about flat Earth. I don't know whether this goes anywhere. It's like people today believing that once upon a time everyone in the world believed the Earth was flat, which is not accurate. Well, so again, these are the dangers of generalities. You could say that most people believed in God. It's just true. So you could say that most people probably had some kind of fear of the end of the earth. They probably wouldn't go out in boats too far because they'd be afraid to be going over the waterfall or something. They just didn't have a concept of spheres floating around in space. Wasn't the first guess. The first guess was something else, that everything was kind of two-dimensional, because that's kind of how everybody kind of dealt with reality, is in 2 dimensions. The whole idea of a space fabric, these kind of, we interact with a lot of things that only have 2 functional dimensions. So people kind of get stuck thinking that way. So they did think that way, generally speaking. Prior to theory, discussion, belief, then accepted proof. See, the acceptable proof. This is the dangerous part, is that word proof. Then finally, acceptance as normal and obvious. Well, I think once they had a reasonable statement, I mean, as soon as they could see the moon a little bit in better detail, I'm sure some people did, just because they saw it from good vantage points, and you can look at it and you can sort of see it's round because you can almost see the texture of it, and get the idea that it's a sphere. It does occur to you, and certainly if you look at it with a telescope, it becomes kind of obvious. So I don't know if this is then isn't now. This is the idea of, okay, you want to have a conversation about why people make mistakes and why some mistakes become intractable. Like you just somehow, they can never fix the mistake. So I could use the two examples of maybe religion and Benjamin Franklin getting plus and minus wrong. So it was sort of a mistake. Well, you could even do with the constants, in science, and how they don't regularize anything. How they have like 17 different ways to measure a calorie or a joule or a watt or they measure energy in all these different ways that they really would like to have just one standard for what energy is, and they don't, and it's kind of a brokenness. And so I could do the plus or minus thing, right? Something kind of fundamental, and the fact that it's broken, that is, that they mislabeled these things, means that their mathematics has stupid things in it. It has current going one way in a wire and voltage going the other way to fix the mistake. They would be going the same way if they didn't have plus and minus wrong, but because they have plus and minus wrong, they have to make directions opposite to fix that. They would be going this way, but instead they have to go this way, but obviously current and voltage, I would argue, are both traveling in the same direction, and so the mathematics is based on a fake, false. It's describing a not the reality because they have the labels wrong. I could almost argue they have the labels north and south wrong. They should be plus and minus, minus and plus. Anyway, but they don't fix those things because it's too messy. It's too much trouble. It's like America switching to the metric system. They tried, and they couldn't get it done. I think they could have. They could have held out another few years, and it would have been all right. But they gave up because it was too arduous a task. It's so some things don't change because too much is built on it, and they can't afford to redo it all. It's too much work. They're too lazy. They don't think it's important enough. So there's lots of reasons why mistakes aren't fixed. Errors aren't fixed. So, and then things like religion that are really stupid and silly. Obviously it's just some sort of thing where people sort of inherit it from traditional family and traditional culture and all that kind of crap, and they can't let go of these infantile connections to some sort of heritage, some sort of common behavior, ritual, bullshit. So they're never, I guess I would say, yes, there's no good reason for intellectuals. I mean, people who want to pretend that they're trying to be smart, trying to be accurate, and trying to be careful, for any of them to endorse mistakes being written in stone and being and accepting never fixing them. It's just obnoxious to structure and reason to think that you can get away with just leaving the broken bits in. It's leave the glass in the food. You break the glass and there's glass in the Jell-O, and you just scoop up the Jell-O and say it's okay. It's only got a little bit of glass in it. Well, no, it's not okay. All right, so that's enough of that. I think I covered it. So where was I? Next, okay, we'll move on to this, I guess, the Feynman paper. Well, maybe we do Sean Carroll first, but this Feynman thing's a little more complicated. We'll do a little bit of it anyway. Hopefully I have enough volume to see.
Is
Yeah, it's probably enough. Okay, so he's answering comments on his first video on one of these big ideas of the universe, and the idea was conservation of momentum mostly. So he's attempting to add some clarification and extra value, and it's I think he did a fine job of explaining certain things very well. I mean, he's a good teacher, but some of the stuff he adds is just horrible. So I mean, the stuff that's completely unproven and untested by any process.
once an object is moving, if nothing acts on it, if no force changes its velocity in it.
Right. So he doesn't think of force as a thing. So this is like the key thing that's missing. He doesn't think that there's any mechanical thing worth noting or worth considering or worth understanding about what is exactly the nature of why two things react to each other. So this thing he says a force. Now we know this force exists between two electrons. All right, so we know how it functions. We know what it does. It causes the electrons to separate at a very specific, in a specific way, by specific rules. And the rule would be consistent with the R rule, essentially, for close contact charges, which means is half the distance, half the pressure. So it can be simply illustrated as, yes, if I thought of these as ping pong paddles and I thought of something between them as being some indestructible momentum, and it just went back and forth between them, I would get the R rule quite simply through the process. If I bring them twice as close together, there's twice as many impacts that have exactly the same transfer of momentum each time it happens. We don't have to worry about how it transfers. We're just going to say it hits it, okay, and it forces it to move. And so we don't bother figuring how or why that happens. It's just a fact. Like I said, I think that can be explained also, but I just mean, just if you take this simple mechanism, this simple idea of a moving particle moving the speed of light, it answers the question of why the two electrons fly apart and why they do that by this specific rule. But he doesn't think this thing is a thing. He doesn't think it's a piece of energy bouncing between the particles. He doesn't think of it as anything but some sort of ESP, some sort of thing that just happens to things. So when these things get closer, somehow they know to repel twice as much. And, when they get twice as far apart, they know to repel half as much as before. So they've just taken this fundamental kernel out of the equation and pretended we'll just call this F. And, it's not, it's sort of a critical mistake to think you can say, I'm going to take something fundamental out of the equation. It's like taking potholes out of streets and then pretending you can make equations and, you don't have to account for the fact that potholes get made by cars driving on the streets.
Anyway, then the velocity will just keep going. The particle will keep going in a straight line with constant velocity, whatever that velocity is going to be. There's no...
Right, so this is another key thing where he'll say particle as if it's, and that will mean anything. Okay, particle means truck, particle means wrench, particle means snowball, particle means anything you can make. And I would argue that there's a fundamental difference between the complex object, the box of chocolates that has lots of atoms in it, okay, and you're going to take this thing that has lots of particles and lots of arrangements between protons and electrons and throw that into space, and the difference between taking an electron and saying, let's throw that into space. those two events are different. What electrons are doing inside of atoms is different, okay, than what the big objects are doing. So they've sort of broken the idea that atomic structures are obeying fundamentally different rules than subatomic structures. That the space the electron exists in, the world they exist in, maybe doesn't work. Maybe this idea that electrons just go perpetually doesn't work. That they do in fact slow down and stop. That we can't make an electron gun. We can't shoot electrons at Alpha Centauri and have any realistic hope they're going to get there. Just can't do it. They can't just point the gun and shoot them. It doesn't happen. The only way you can move these electrons in space is to make them part of a plasma that has protons and electrons in it, and push them as a group of atoms. You can get protons and electrons to places that way, but you can't just shoot them out of a gun. So it's sort of a disconnect to, this is proven physics, throwing wrenches into space. That you can prove. This they haven't proven, that all particles do this thing. All particles are capable of being given perpetual motion. They don't have proof of that one.
Universal velocity for things moving in a vacuum. Okay. Then there's a couple of questions which added up to the idea.
And this sort of gets to Newton, right? So Newton came up with these force laws, but Newton had no way of considering subatomic particles. He had no way of understanding that maybe they don't do that. Maybe there needs to be a structure for you to be able to create this idea of an engine, something that can keep moving through space.
Where does energy or momentum go? Where do they go? And this makes more sense for momentum. So where does the momentum go in a collision? And depending on how familiar you are with conservation of momentum, etc., this might be a really good question or a perfectly obvious question. The momentum doesn't go anywhere, it's conserved, right?
All right, so what's being conserved is, I would argue, is motion. And as I've argued, we know that the smallest things have motion at the speed of light. So we know the photon type object has a perpetual motion, that the energy of the quanta of the photon, I would argue that's made of more than one quanta, of course, frequency, but that the idea would be is that energy is in this form, the stuff moving the speed of light. So magnetism and gravity would also be made out of this same mechanism that's moving the same speed. It just makes sense to say that's reasonable as speculation, that if one moves the speed of light, that the other thing's moving the same speed, that it's probably made of the same kind of nature, that it's a quanta of something. And that the difference for gravity is that, gravity's only single bits moving at the speed, not at a frequency, a consistent frequency. It's at a inconsistent frequency. Therefore, it can't be seen, can't be detected by our radio antennas and whatnot. And that the other catch would be things like magnetism just means that you have segregated two types of this stuff moving at the speed of light, and these two types can be separated. They can come as a mixed group, where there's a mixture of the two, or it can, through a magnet, be segregated, where all the green bits go one way and all of the red bits go some other way, and now can affect things that are affected by charge, like the electron and the proton, which are also sensitive to this mechanism. So you can create a simple mechanism that makes it understandable that what you're really saying is there's stuff moving the speed of light, and then big things, pieces of matter, move some lesser speed. So essentially the speed of light has gone inside of them, is playing a little bit of a game while it's inside. It's doing a little pinball. It's bouncing around a bit and causing this thing to move, but not necessarily move one way. So it's trapped. So it's causing energy this way, and then it causes some energy, motion that way, and then causes some this way. And overall, it creates a little extra energy this way, because it goes this way a little bit more than it goes this way. And so the end product is this thing moves 2 miles an hour. Okay, this thing's moving the speed of light, incredibly preposterously fast. But the big piece of matter is moving some lesser speed. Even the electron, generally speaking, doesn't move the speed of light. It moves something less than the speed of light. So somewhere, okay, you've taken one speed and spread it essentially over something bigger than it, and you've gotten less out of it. So it's like a tiny snowball hits the big giant snowball. It makes it move just a little tiny bit. So the snowball was moving 50 miles an hour, but the big one's only going to move 1/50th of a mile an hour. Got my chalk. All right. Good more.
But think of it from the point of view of one of our balls of silly putty in a inelastic collision. Okay, so the balls come toward each other, they smack into each other, and then they just stick into a big blob. Okay, so
they don't really just stick in a big blob, right? Would be the simple answer. They move all the little bits inside of them. So all the little bits spread the energy. So instead of being elastic and hard and just bouncing off of each other and going in different directions as whole objects, instead you've taken the speed, all the little bits of momentum, or all the little bits or have the momentum. The little bits inside of this have the momentum, and you see that it goes out to the external world. It's still out here. Well, in the elastic collision, where this stuff is now mush, it's gonna so all you're gonna do now is crash these two things into each other, and you're gonna have the same effect. Even though it won't look like it, it's going to be the same thing in the sense that the two objects will collide, and they're going to move. All of these little bits are going to move, and then the movement of all of those little bits is going to create heat, radiation, okay, that's going to leave in all kinds of directions likely. And so instead of converting the energy into motion this way with a lot of mass, you spread the energy in all these directions with very little mass. Alright, so that would be kind of the way to think about it. It's still all motion, and in whole you still have a closed system that has so much proximity in it. It has so many little bits of matter so close to each other, which means the energy between them is bouncing back and forth, back and forth, back and forth at a rate. And all you're going to end up with is, well, now I'm going to start separating them, okay? And they'll get further and further apart from each other, and the energy becomes less and less relevant in terms of, it's still trapped inside of these things moving, don't get me wrong. That's why it's such a small percentage of the universe it's affecting. But the same idea is going to happen. It's a closed system with a certain amount of proximity, and until you make the proximity much, much further apart, you can't get rid of that energy. And like I said, in the hard objects, you've still got most of the energy still in the form that it was in before, in terms of it's just momentum in one direction. And the elastic collision will allow you to spread the energy, to scatter it in a whole bunch of directions.
There's momentum in each individual blob beforehand. They add up to zero because momentum is a vector quantity. So there's momentum this way, momentum that way. Since they're pointing in opposite directions, the total momentum is zero.
All right, so there is no zero momentum. So it's just, I think it's just flat out wrong. There's a ton of momentum in terms of the reshaping of the object. And every time it reshapes with the rest of the universe, it pushes in and pushes out. That's work. And that work will have an effect on the rest of the universe. Things will hit this thing sooner than they would have hit. It's going to create proximity with the rest of the universe. It's going to, every time it expands, it's going to say, I'm closer to some other object in the universe. And that's a real closeness. It's not a fake closeness. But it's infinitesimal when you spread over almost this idea of an almost infinite surface, in the terms of there's, a zillion atoms involved in this interaction, and you're taking energy that was, in traps, and you're untrapping it essentially. You're scattering it, you're allowing it to get free and interact with all the other little bits, but it does leach out just as much as it leaches out in the other interaction. It is leaving. It's just leaving in little tiny bits of radiation rather than in a clump of radiation.
So a
clump of mass.
Total momentum is zero both before and after the collision. But if you think about momentum as a thing, as a substance that sort of inheres in one of the particles, in one of the blobs, then when you're living on one of the blobs, your momentum disappeared. You had momentum, then you hit another blob and your momentum went away. Now there's...
Okay, but there is no... See, it's just wrong to think that your momentum can be destroyed, because it can't be. The momentum is made out of a force moving, a photon, a piece of quanta moving. And you can't kill the motion. So the motion has to still go somewhere. And the fact is, heat is it going somewhere. That's how it's going to escape.
The total zero momentum. Where did it go? This is exactly why you should not think of momentum or energy as things, as substances.
Right, so this is exactly why you're wrong and your physics is garbage, is you tell people what not to think when it's exactly what they should think. If they want to be able to understand physics without having to get a degree in ESP or magic, yes, you have to understand that what's really at work in the universe is a bunch of indestructible energy, and the energy is in the form of a photon. It's in the form of a quanta of momentum, and as I just explained, that quantum can explain gravity and magnetism and all the effects we see, and it all is real energy, and there's no way to cancel it. You can't just say, I plowed this into that and I made zero. You never do that. There's no anti-energy. There's only energy. So you either create this and this, or you create this and this, or you create this and that. But there aren't any other choices. It will, on the nuclear level, on the energy level, one of these reactions is going to take place, and all you're saying when they're elastic objects, hard objects, is that they just go one direction and they go this direction. And when you're saying they're elastic, you're saying, okay, it goes this, 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 this. It gets spread out over the whole distance. So it's just the difference between a laser beam and a regular light bulb. One, you've concentrated the mass and momentum in one direction by keeping it a solid object. You've contained it and not allowed it to spread. And in the other, you're allowing it to dissipate. But you never destroy it.
As fluids. There was a time when that was a conventional, popular way of thinking. Things like heat was thought of as a fluid that moved from one thing to another, but it's not the way to think.
Yeah, it is. It is the way to think. Heat is a real process. It's real atoms that are getting pushed off the surface of something. It's moving the atoms in the atmosphere. When you absorb heat from something, you're, from the atoms in an environment, you're absorbing their movement, their momentum. The heat is a real thing. It's a real force that they had to capture. The real force the atom was sitting here minding its own business, and a piece of energy went into the atom. So the energy was going the speed of light. The atom is going some slower speed. And so essentially it's because it's in a trap, and it flies in more directions than hitting this surface all the time. It hits others and bounces around and doesn't go in a straight line while it's captured. And so it's like a bird in a cage. It's still flying. It's just bouncing off the walls of the cage until you let it go again. And the cage will move because the bird is in there. So that's just all that's really happening. You're caging the energy. It's the total amount of movement is still going to be the same.
Momentum is not a thing, it is a property.
No, it isn't. It's a property, certainly, of a system, but it's not a property of cage. Cage doesn't have bird in it. Cage is capable of holding bird. So you can say matter has the property of being able to trap energy, catch energy, hold energy, but it doesn't have energy as its property. It doesn't have any birds until you put a bird in the cage. And I think that's the more rational way to understand it. It's a real thing, energy. It's moving at a real slow speed, demonstrating its realness. That's one of the ways you can figure out something's real, is that it takes it time to get someplace. Unreal things wouldn't need to take time to get anywhere.
Momentum is the answer to the question. When you take the velocity of the object and multiply it by its mass, what do you get? Okay? So there's no place that...
So again, the mass is what has to be moved. The mass is what the one piece of quanta going the speed of light has to integrate its motion over. So the mass is just telling you how many quanta it will take to move the mass 1 inch. So that's the theory. That's the function. Is how many quanta does it take to hit an atom? What's the average amount of energy needed to push an electron 1, micrometer? Blah blah blah. Whatever standard you put it in, the truth is the mass requires a certain amount of quanta to hit it from one side more than the other side for it to gain a certain amount of velocity. But it only gains it by capturing it, by putting birds in the cage that are going the right way. Well, see, I don't want to say that. See, it doesn't collect birds. It has birds that are just sitting in the cage. You could say it starts its trip by having just as many birds flying that way in the cage as they're flying that way. So the cage doesn't go anywhere, it just wobbles. And that what you can do is change which birds you have in the cage, right or left birds. So now you can have more left birds, and then you'll go left.
The momentum left. The total momentum of the system is 0 before and after. There's no law of conservation of the momentum.
That's right. So there'd be no reason to say the total momentum is 0, because we know the things are moving, so they have momentum. So I don't even know why you would say that. The total momentum of the system is never 0 if anything's moving. You can't have 0 momentum when you're moving something. So you can't move an atom or an electron or a proton and have a 0 momentum.
Of individual pieces that are interacting with other pieces. This in fact leads to exactly the next question, which is this whole set of properties we talked about of conservation laws makes sense if you have a closed system, a system that is not interacting with...
All right, so obviously it's just how big you make the system, but so there's no point in saying closed system. You're saying isolated or sectioned system. So we know that it's a closed system in a sense when we're saying, what are these two objects going to do? Well, you obviously took the moon out of the equation. You took Venus and Pluto and all the other stuff out, but you just want to know these things have X momentum, and they're going to move into each other, and all we want is the relative difference. Both of them are being affected by the moon, both of them being affected by Pluto, we can eliminate all of that crap and just say, what's the interaction between these two things as an isolated question. Now, obviously, this thing will be a little tiny bit closer to the moon than this thing. It's going to be an infinitesimal amount of distance, and there's going to be lots of all that. So you could say exactly there is no closed system, but for the sake of point 0.00000000 places of accuracy, I don't have to worry about any of the other influences. I can understand this simple system and say what happens to the energy of these two things when they collide. And I can add it up and figure out that no matter how they collide, no matter what they do, no matter whether this breaks apart or this breaks apart or they both meld together, they do whatever they do, the same amount of momentum as incorporated as actual force moving the speed of light, or a piece of matter moving something much less than the speed of light, the actual amount of force those things will be exactly the same as what they started as. So whatever's in the box, whatever momentum is in the box of this, exactly the same is going to be in the box after they hit each other. The box is still going to contain a certain amount of stuff moving the speed of light and a certain amount of mass moving much slower. And that's the total momentum, and you're never going to change that.
Anything else. Of course, the momentum of a particle can change if I push it, right? If some force acts on it, then of course no.
So he's using words, right? You don't say I push somebody with my ESP. So, I mean, obviously, this idea that this force is a nothing doesn't work. You don't push something with nothing. You don't push something with the idea. I'm an electron. You're an electron. We don't like each other in principle. You don't push something with a principle.
Momentum is going to change. That's exactly what's happening here. This other blob is coming in, hitting the first blob, and their individual momenta both changes. So that's where it goes. It doesn't go anywhere. It's not.
So to say their individual momenta changes, it doesn't. In the sense that, yes, one can be going 60 miles an hour and the other could be going 40 miles an hour, and when they leave, this one will go 60 and the other one will go 40. So they can exchange pieces of a momentum, but never does momentum cancel, never does momentum disappear, or never does the element that's controlling it is this a quanta going the speed of light. The number of Q's going the speed of light, okay, C, that's what the matter has in its cages. That's the E equals mc squared. That's what it's holding all the time, is some measure of that, some amount of that. The electron always has a certain number of birds in the cage. And all you're doing is saying, well, the total system is going to be, I can have 10 birds going this way in one electron, and over in here in this electron I can have 10 birds going this way, and then over in here I can have them go 10 birds going this way. I have exactly the same amount of Q's when I'm done that I started with. All I can do is change who's got which birds in their cages, or how many birds are free. But that's all. The total amount of birds is always the same. The universe has so many birds in it, and that's it. There's no getting more and losing birds. That doesn't happen, so to speak. I mean, I can't speak for the whole universe. I'm not pretending to know how far it goes, or whether it's a bubble or a sphere or what it is. It doesn't really matter. I'm just saying, for the sake of argument, any part of the system we choose to make a box around, and we assume nothing to be going in and out of the box always contains the same number of Q's, no matter what happens in the box. Explosions, no explosions, it just doesn't matter. The Q's are always there.
The thing that has to go somewhere. It's just a quantity, a property that you calculate. The bigger question then is, what about the universe? Okay, is the universe a closed system? Does the universe have a net zero change in momentum and energy and electrical charge over time? So I think the simplest answer to that is yes.
Yes, so there's no point in answering it. So just as I qualify the fact that, yes, I can speculate about what the universe might be, but we just can't know that. The whole universe might be a speeding bullet in some other universe. I mean, it's just there's no point in talking about what it is as a system, whether it has a bias built into it or not. It just doesn't matter. For the point of the argument, we can make our boxes much smaller than the whole universe, and we can know that we can make a theoretical box that isn't open to external manipulation, and we're just going to consider what's in the box. And we know that whatever's in the box, no matter what happens to it, it's still the same amount of Q is in that box. No matter what the things do, you never gain or lose a bird.
By definition, right? If we thought that the universe was being acted on by something else, okay, if there was something other than the universe that was...
All right, we've probably gone far enough, because like I said, this is the part where physics just starts talking out of its ass, and it's not very constructive not to say it could be exactly the opposite. It could be, because it could be a lot of different things. But the thing that we know is it's behaving as a closed system. It's behaving as if it has every appearance of being a consistent machine that's obeying conservation. All right, so we go to this paper. All right, so this is Feynman's paper, and she's going to attempt to summarize the basic argument Feynman's making and his effort to find a mechanism for getting to a more expedient answer to fundamental questions about where the energy is in these systems and how to best analyze the consequences of these collisions in these very small boxes where electrons and protons are interacting.
Two problems. One is that we have a self-interaction of a charge with its own field, and when we do calculation...
I have to say, I really do love her voice. Yeah, well, the rest of her is, not bad either, so... She is charming. Tibees. Not a very good name, but, whatever.
Regarding this, they predict that a point-like electron would have an infinite mass, and this is a problem that exists even in the classical theory.
Right, but this is a problem in all of their physics, is because it doesn't have any mechanical function. They're almost saying that the process of producing my ESP makes me have a counter reaction where I move away from the object because my ESPing forced me to have a reaction. And, they're trying to turn this magical property of a force, and they're trying to explain why does this thing that we think is vaporous and indescript and field-like, well, why does it have those kind of reactions? Why is it like throwing a baseball? Shouldn't it not be that way? So because they don't have a model, a mechanical model, then they're capable of being confused and thinking, well, because the electron is radiating this energy, there could be like this infinite problem where, because it's pushing something out, that it has an infinity problem, in terms of the equal and opposite reactions, or something like that, and like it would implode on itself because of its own process of producing all this energy, where it didn't really produce it. Okay, it's just a reflection of what came in from the outside. It didn't make the energy. So it's this problem of making and destroying energy, because they don't understand the real conservation. It isn't like it goes into the well and disappears and then it comes from some new place to fill the void, like their gravity theory. Their gravity theory thinks the energy just dies in the black hole, and that there's some infinite well that'll just keep filling the black hole. And there's no infinite well. So this is the problem with their mathematical models, is their mathematical models don't understand that, no, there is a certain amount of pressure in the universe. It's 100 pounds per square inch, whatever you want to call it. There's a certain amount, okay, of of stuff, density of stuff in the universe, and you can't make extra gravity beyond that to its maximum. So that's as high as you can go. You can't go any higher than what can the universe produce as a maximum pressure. You can just find places where there's less pressure and places where there's a little more pressure, but you can't have an infinite amount of pressure. You can only increase it, like you can make it 200 pounds, but you can't make it 1,000,000 pounds. You can't collect the energy of the universe and make it all go down one way, because there are birds flying in all directions. There's not enough birds. You can only take a certain percentage of the birds and have those fly in one way all together at one time or in one place. But you can't take all the birds that are going every which way and force them all to go one way.
And the second problem that I can tell is that there seems to be something to do with an infinite number of degrees of freedom of this electromagnetic field. So you can see Feynman wants to solve both of these problems by just doing away with the idea of the field altogether. In fact, he thought that the idea that a particle could act on itself is in fact a silly one, and instead suggests that electrons cannot act on themselves, they can only act on other electrons.
Well, there he had something right? So that's sort of the kernel of recognition. The idea of pretending that I can understand the field by pretending there's no field, that seems kind of silly. So it's just basically saying I'm going to make an effect theory. I'm just going to say there's an effect. Okay, somebody runs out of a building. Okay, so that's the effect. He doesn't. He wants to pretend it, and we sort of have this idea that the other effect is that the word fire happens. The word fire happens, and then the effect is something runs out of a building, and he wants to eliminate the process where somebody actually has to yell fire, okay, and it has to be heard, it has to get to the person in the building, and then the running happens. So he's breaking the chain of cause and effect by saying, let's just worry about these effects. The effect of I hear the word fire, and I see run, and there's a whole process that's connected there that he's saying, well, that's too complicated, I can't figure it out, and mechanical mechanisms don't work no matter what we try, we're smart, we can't figure it out, so let's just cut that part out and let's see if we can just find an equation that causes fire to be said and causes run to happen. And yeah, it just breaks the obvious. So I would, again, just point out the obvious, that if you just take a simple mechanical quanta and move it back and forth between an electron, you will create the R rule. You'll create twice as much energy when they're this close together as you have when they're this close together. Because you've increased the distance, that the force will not be hitting something. It will be traveling rather than hitting. So you make more hits, less travel, more hits, you have more energy. You have more impacts with a surface, more experiences. And that's all you need to explain the behavior of electrons.
There's no field, just a direct interaction between charges, although with a delay. For example, he says that if an electron in the sun were to shake, then an electron in your eye would shake 8 minutes later. There was one big obstacle.
Right, which is perfectly suitable. It explains exactly what's happening. As long as the force gets to your eye at the speed of light through a photon, that's what you'll do. So you need a photon to transmit it. You could transmit it with another piece of energy like gravity and all these other things that are moving exactly the same speed, and they will wobble the electron also. They just won't wobble it the same way. When you wobble with a frequency, you do a specific thing to electrons that causes atoms to misshape, and when the atoms misshape, they cause electricity, and in that sense you can detect photons at a frequency. I don't think anything else has to be said. There is no problem with the fact that it takes time. if you just understand that the distance is both trips. It has to go one way and then it has to go back the other way. So it's the round trip that's defining the energy. How long is the round trip? And the round trip obviously has this way and this way in it. Two opposite ways. They're traveling those opposite ways effectively at the same time when there's more than one of them involved, more than one quanta of energy.
To this idea, however, see, when a charged particle, such as an electron, is accelerated, it emits electromagnetic radiation. But this radiation carries off energy.
So again, this is what they say, right? And it's a model, doesn't say anything, doesn't explain anything about how it emits this radiation. And the truth is, it's not really emitting any kind of radiation. When you move the electron is in a constant circumstance where it's reflecting the world that's hitting it. Things are coming at it and hitting it. When I move the electron to a new location, I change how soon these interactions will take place, and I change where the force will reflect to. So it reflected here, let's say, when the electron's here, and the force is going to be reflected here when the electron hits it, when the force hits it here. It's two different locations are going to be affected by the energy depending on where the electron is. So the electron's producing nothing while it's moving. It's always reflecting the universe, but obviously when it's moving towards you, okay, if it's moving towards you, it's going to be reflecting energy at you sooner than it would have if it stayed where it was. So it's obviously creating more energy between you and it as it's moving towards you. But it didn't produce the energy, if you understand what I'm saying, right? It didn't produce anything. The ping pong bottle pulse produced the energy, right? The electron moving doesn't produce anything. It didn't make anything. It just made it so there's more interactions happening between you and the next electron. It itself didn't make the photon. The fact that you created more energy between the two things created the likelihood that you can excrete more energy. So if there's a little leak in this process, you can understand that you'll leak more. The more pressure that's in the bottle, the more water will come out the hole. So the more you'll leak, and that's this thing called a photon.
Energy and momentum, which by conservation must result in work being done back on the original charge, back on the original electron. It's referred to as radiation resistance, radiation reaction, self-force, or the Abraham-Lorentz force, and you have to do extra work to account for that energy.
Right, so they're saying work is being done, but no, what's really happening is as the electron's moving, it's also it's moving into more force hitting it than was hitting it before, and that's its loss of energy. It's losing energy because it's moving in a direction that's causing it to hit more stuff from ahead of it than it's hitting from that's pushing it from behind. So it loses its momentum.
This can be accounted for in calculations if you have an electron acting on itself in a field, but since Feynman is not...
So again, this acting on itself thing, it can never act on itself. It's just a mirror, and all you can do is bring another mirror closer and closer, and you have light trapped between it, and that's all that really is. You don't need more explanation than that. So I don't think there's anything else in this that's terribly interesting, because it just gets into Hamiltonians and all kinds of abstract mathematics used to explain something that I think mechanically can be understood simply as the energy between electrons isn't something electrons produce. The energy between magnets is not something magnets produce. It's just how they filter the energy that goes in, the quanta that goes in. The energy that pushes the Earth into the sun is a byproduct of the fact that energy is being absorbed by the Earth and the sun, and that absorption of energy, that quanta of birds being exchanged, means that the birds aren't getting where they were going, and they're not hitting the object they should be hitting, and therefore the object is getting hit by more birds going one way than the other way, and therefore moves. And so all of it can be explained as a simple mechanical process of filtering bits of force moving the speed of light. All you need is two forces, two kinds of force: blue birds, red birds, left birds, right birds, however you want to describe it. Two kinds of cage, electron cage and proton cage, and two kinds of interaction. In simple words, the interactions would be it reflects off and the bird goes the same way it came, the opposite way it came in. It releases a bird going this way for a bird that goes in this way. Or you can have the reaction where you put a bird in this way and this bird goes that way and this bird goes that way. Alright. So, yeah, I think that's enough of a video. So, till the next time and such.